Okay, in this podcast we're going to be learning about solutions. A lot of this, again, should be a repeat for you from Honors Chem with a little bit more depth. Okay, so solutions are nothing more than homogeneous mixtures of two or more pure substances. We usually think about it as dissolving a solid in a liquid, but it can in fact be any combination of gas, liquid, and solid. In a solution, the solute is the thing being dissolved, and the solvent is the thing doing the dissolving. Just a couple of terms. When we're talking about dissolving a solid or a gas in a liquid, let's say we're dissolving sodium chloride in water, we talk about the solute being either soluble or insoluble. When we're talking about dissolving a liquid solute in a liquid solvent, instead of using the term soluble and insoluble, we use the term miscible or immiscible. So acetone, we would say, is miscible in water. Okay. So in a solution, the intermolecular forces between solute and solvent particles, the two when they're combined, must be strong enough to compete with those between the solute and the solvent. So the solute and the solvent start off with some attractions for each other, and what this is saying is that the solution must have interactions that are strong enough to compete with those of the solute or solvent alone in order for the solution to occur. So let's take a look at how solvation actually occurs. Here we see the water being polar is attracting each of the ions and plucking them off, right? So the negative side of the oxygen on the water is attracting the positive sodium ions, and the more positive hydrogen parts are dissolving or taking away the more negative chloride parts. And you end up with what's called solvated ions. Also, when water is the solvent, we call them hydrated. Okay, so that's what actually happens during solvation. Okay. So how does it actually form? Well, we have an ionic salt that's soluble in water. It's because of the ion-dipole interactions, and what that means is this sodium has an ion, right? It has a positive charge. And we have this dipole from the polar water, which is acting as a solvent. The more negative side of it is attracted to the sodium plus. So it's this strong ion dipole interaction that allows the solution to form, that allows the sodium chloride to dissolve. And on the same case, we have the chloride negative side attracted to the more positive side of the hydrogens from the water, also causing this ion dipole. Okay, so these forces must be strong enough to overcome the sodium chloride being by itself and the water to be by itself. So there are three things that affect the energy of the solution. If we start off with the solute molecules, we need to put energy in. Always requires energy to separate the solute molecules. Okay. We also need to separate the solvent molecules, and that always requires energy being provided, energy going in. So if this was water, you know there's water attraction between water molecules, and breaking those attractions to make room for the solute is what is required here. And then there's some energy associated with the formation of the solute and solvent. And that generally, always will result in a decrease in energy. So that will be exothermic. So these two steps are going to be endothermic. This step will be exothermic. Now, the solution process could be exothermic or endothermic. It depends on the magnitude of these two versus this. Okay. So we need to separate the solute and the solvent to form the solution. Okay? So it's going to take energy to separate them, and once they're separated, they're going to come together. So whether or not the heat of solution is positive or negative depends on how large separating the solute, separating the solvent is, and how exothermic then the coming together of the two are in solution. And in this case, it is an exothermic process because the energy released from the particles coming together is greater than the energy required to separate the solute and the solvent. So, in fact, there are some processes where you are making a solvent and the net process is endothermic. And one of the things we learned about in when we discussed equilibrium was that generally exothermic processes are those that occur spontaneously. Unless the energy of the system is lowered. So we know that in some processes, ammonium nitrate, for instance, heat is absorbed and not released. And actually, ammonium nitrate is used in the cold packs, right? The instant cold packs, because they get cold, right? And that's an endothermic process. So why does that happen? Well, it turns out it's not just the energy, but it's also entropy that determines whether or not a solution or a solute will be dissolved in a solvent. So increasing disorder or increasing entropy also lowers the energy of the system. So one factor that does result in a solution forming is increasing entropy. Okay, so either decreasing of the energy, delta H, or the increasing of entropy. So even though the enthalpy may increase, the system can still decrease if the system becomes more disordered. And here we have a case where it's probably going to be endothermic, but we still have a solution form. Okay. In this process illustrated below, water vapor, right here, reacts with excess solid sodium sulfate, the ionic crystal here, to form the hydrated salt, sodium sulfate decahydrate, right? Essentially, all of the water vapor becomes enclosed in this reaction. It becomes enclosed in the ionic crystal. So if we consider our system consistent of one crystal of sodium sulfate and 10 particles of water, does the system, or essentially 10 moles of water, does the system become more or less ordered in this process? Well, it's obvious that we have all these waters around here, the sodium sulfate here, they come together like this, just one thing here, so this is going to become more ordered. And if it becomes more ordered, then the entropy is going to decrease. So what happens to the entropy of the system if I open the stopcock and I allow the nitrogen and oxygen to mix? Well, obviously entropy is going to go up because there'll be more mixing between the two, more disorder, which is what entropy is all about. Okay, so one of the things you have to be careful of, sometimes people will actually incorrectly exchange the terms react and dissolve. They're not the same thing. So if I were to put, let's say, metal in hydrochloric acid and the metal goes away, it does not necessarily mean that it dissolved. It could mean that it reacted. Okay, so you got to be careful of that when you're looking at a change. So dissolving is actually a physical change because you can get the original solute back by evaporating the solvent. So if I dissolve table salt, sodium chloride, in water, it dissolves. If I boil that water off, I end up with sodium chloride at the end. So it's a physical change. It's reversible. I get the solute back. In a chemical reaction, I don't. Okay? So if you can't get it back, it's reacted and not dissolved. Alright, so we can have solutions that are saturated, unsaturated, and supersaturated. In a saturated solution, the solvent holds as much solute as is possible at that temperature. So it's like a sponge. It's completely saturated with as much as it can possibly hold. And the dissolved solute is in dynamic equilibrium with the solid solute particles. Okay. An unsaturated solution is one where I can still hold more, I can still take more solute and dissolve it, right? So here I have some, let's say, some sodium chloride, but there are still a bunch of waters that don't have an ion with them. So unsaturated means I can still take more solute. There are some solutions that can become supersaturated, and if they're becoming supersaturated, that means the solvent can hold more solute than is normally possible at that temperature. And they are very unstable, and just tapping the solution can cause them to crystallize, or adding just a crystal, which we call a seed crystal, starts the crystallization process and gets this whole process started. Doesn't take much. It's kind of a cool thing. When we talk about what results in a solute being dissolved in a solubility, we talk about this like dissolves like. And basically what that means is, when we're talking about what's like about two things, we're talking about whether they are polar or nonpolar. So polar substances tend to dissolve in polar solvents, and nonpolar substances tend to dissolve in nonpolar solvents. Okay? So the more similar the intermolecular attractions, the more likely one substance is going to be soluble in another. Okay, so for instance, glucose, which has hydrogen bonding, this is glucose, right, is very soluble in water, because water also has hydrogen bonding, very polar. They are both very polar, and therefore they are soluble in each other. But cyclohexane, this molecule here, which is totally nonpolar, is not soluble in water, because water is polar and this is not. So vitamin A is soluble in nonpolar compounds like fats, okay? Because this is mostly nonpolar. Whereas vitamin C, which is quite polar, is soluble in water. So let's take a look at trying to identify which will be dissolved in which. So we have two solvents here. We have carbon, let's just go back. We have carbon tetrachloride, and we have water as our two solvents. So we have CCl4 and we have water, and we want to look at which ones will be dissolved in each. So here we have this heptane, and it's going to be totally nonpolar, so it's going to be soluble in carbon tetrachloride. This is nonpolar, right? And this is water is polar. Sodium sulfate, this is the ultimate in being polar. We have positive ions and negative ions. So this is going to be dissolved in water, which is polar. HCl will also ionize, so it's quite polar, and it will dissolve in water. Iodine is nonpolar and will dissolve, therefore, in carbon tetrachloride. Alright, let's also arrange the following substances in order of increasing solubility. Okay, so the lowest solubility is going to be something that is totally nonpolar. So this is going to be the lowest, right? And the highest is going to be, let me see, so we've got OHs, two OHs here, we have just one OH here, and we have a Cl here. So I have two areas where the molecule becomes polar here. So this is going to be the most. And then I have an OH, and I have a Cl. So the O is more electronegative than the Cl. So this is going to be, so this is low, which is 1, and this is 4, which is high. This is going to be 3, and that one will be 2. Okay. Okay, so in general, solubilities in water increases with increasing mass. Okay? And that's because larger molecules have larger dispersion forces. So the larger the dispersion forces, the more like water, which is polar, it becomes. So we know that if you put a solid in a liquid, you are more likely to get the solubility to increase if you heat it up. But in fact, gases in solution work the opposite way. We also know that if you add solid to a liquid, that you don't get much change when you put more pressure on the system. But you do get a big difference when you put pressure on a gas. So the solubility of a gas is directly proportional to its pressure. So here I have a liquid with some vapor pressure, right? There are some gas particles above it, and if I increase the pressure by pushing down on this plunger, basically those gas particles get pushed into the liquid, causing the solubility to increase. Okay? So the more pressure I put on a gas, getting it to go into solution, the more soluble it is. This is what's used to make soda, right? Soda is made under high pressure, and that pressure is used to basically push those carbon dioxide particles into the water. Alright, so let's take a quick look at Henry's law. Henry's law looks at what happens to the solubility of a gas. It's just so here we see the vapor above the liquid, and it's in equilibrium. Equal number of particles going in and out at the same time of the liquid. As they increase the pressure, more and more of those particles have to go inside the liquid. So that's basically what Henry's law says. Alright, so let's take a look at the actual formula for Henry's law. Alright, so what Henry's law says is the solubility of a gas is equal to K, which is a Henry's law constant for that gas in that solvent at that temperature, times the partial pressure of the gas above the liquid. Okay? So the solubility of a gas is dependent on this constant times the partial pressure of the gas above the liquid. Alright, so let's go ahead and try to use this. So we have a concentration of CO2 in a soft drink that we have to calculate. It's bottled with a partial pressure of CO2 at 4 atm above the liquid at 25 degrees C. Henry's law constant in water at this temperature is 3.1 times 10 to the minus 2 moles per liter. Okay, so we want to know molarity, or the solubility of the gas, and what we know is we know that's K times the initial pressure. So the pressure is 4.0 atm, and the Henry's law constant is 3.1 times 10 to the minus 2 moles per liter atmospheres. Atmospheres cancel out. I end up with the units of moles per liter, which is the same as molarity, and it's going to be 3.1 times 10 to the minus 2 times, let me just see, times 4, which is going to give me an answer of 0.12. So it's 0.12 molar. Okay. Alright, let's do this other one. We want to calculate the concentration of CO2 in a soft drink after the bottle is opened and equilibrates at 25 degrees C. And here the partial pressure is much, much lower, right? 3.0 times 10 to the minus 4. So not real surprising, because we have, one is the let's say the partial pressure when the soda is in the can, and then we pop the lid and that pressure is dissipated, right? So we're going to take the solubility in this case is going to be K times the partial pressure, and the K is going to be 3 times 10 to the minus 4 atm. I'm sorry, that's the pressure. And my K, my constant, is the same. 3.1 times 10 to the minus 2 liters, moles per liters atmospheres. Okay, atmospheres cancel out. I'm left with moles per liter. And it's 3 times 3.1, which is 9.3, times 10 to the minus 4, and minus 2 is minus 6 molar. Okay. So for most solids, if I increase the temperature, I can dissolve more. That's what this graph is saying. Okay, we've seen these graphs in Honors Chem when we looked at solubility curves, and we have some practice reading those. This tells me how many grams of each of these ionic compounds or salts are dissolved, can be dissolved in 100 grams of water. And most of them increase with increasing temperature. Although interestingly, sodium chloride increases very little. Okay. But the opposite is true for gases. As I increase the temperature, the amount of gas that will dissolve goes down. So this is I like to remind people to think about their soda. If you take your soda out of the refrigerator, once it's been opened, is the amount of carbon dioxide that remains dissolved greater or less than if you left it in the fridge? Certainly if you take it out of the fridge, we all know that it's going to lose its fizz a lot faster, right? So gases come out of solution when it gets warm. This is a problem with warming of riverbeds and lakes, especially when they're around industrial complexes. In that there's remove some of the oxygen, and it will result in fish kills. Okay. So now we're going to talk about different ways of expressing concentrations. These are all pretty easy, but there's lots of them, lots of questions like these going from one way of expressing concentration to another on the AP test. Okay. So let's just go through them, and then we'll do a couple examples. So mass percent is just mass, like the mass percent of anything. It's the mass percent of component A is the mass of A divided by the total mass. And if I multiply it times 100, I get a percent. I can measure in parts per million and parts per billion. I do that when I have really tiny concentrations. So this is simply the same ratio here as the previous one when it was the percent, mass of A versus the total mass, and I just multiply it times 10 to the 6th to get it down to the billions. I'm sorry, the millions. And if it was per billion, it'd be times 10 to the 9th. Okay. Okay, so part per billion is just the same thing by 10 to the 9th. Okay, so let's say a solution is made by dissolving 13.5 grams of glucose in 0.1 kilograms of water. What is the mass percent of solute in this solution? Okay, so I have 13.5 grams of C6H12O6, and I have a kilogram of water, or 0.1 kilograms of water. So I've taken that 0.1 kilograms of water, I've added this 13.5 grams of glucose. So my total mass is going to be 0.100 kilograms of water plus the 13.5 grams. I'm just going to take 13.5 times 10 to the minus 3. That's my easy way of converting that to kilograms. Kilograms of glucose. Okay, so I'm going to end up with 13.5 divided by this, and that is going to give me, and then I got to multiply times 100 to get it as a percent, and that comes out to be 11.9%. So it's simply 13.5 divided by 0.1 plus 13.5 times 10 to the minus 3, divide the whole thing, multiply the whole thing times 100, and I get 11.9%. Alright, for B, a 2.5 gram sample of groundwater was found to contain 5.4 micrograms of zinc ions. What is the concentration of zinc ions in parts per million? Okay, so let me see, I have 5.4. Let's put these both in grams. This would be, if it's microgram, it's going to be times 10 to the minus 6 grams of my zinc over my 2.5 gram sample, which assumes that everything's in it, plus the water plus the zinc, right? So that's going to be, and I'm going to take all this and multiply it times 10 to the 6th. And when I do that, these 10 to the 6th cancel out, and I end up with 5.4 over 2.5, and that comes out to be 2.2 parts per million. Okay. Alright, mole fraction, we've used this already a couple times when we looked at some AP problems. So in this case, it's just like the percent moles, right? But we don't use multiply times 100. So mole fraction is just moles of A over total moles in solution. If we wanted the mole percent, we would multiply this times 100, but we're just stopping here. So in some applications, this is just a warning about making sure you know how what the question is asking. One needs the mole fraction of the solvent, not the solute, so you need to make sure what quantity you need. Molarity we're all used to, at least you should be. We've been doing this for a long time. It's moles of solute divided by liters of solution. And because volume is temperature dependent, right? Even for a liquid can change volume depending on the temperature. Molarity can change with temperature. So when it's important to have molality, it's important not to change with temperature. We use molality, which is the moles of solute over the kilograms of solvent. Okay, so let's take a look at a calculation of molality. Alright, a solution is made by dissolving 4.35 grams of glucose in 25 milliliters of water. Calculate the molarity of glucose in the system. Water has a density of 1 gram per milliliter. Alright, so I have 4.35 grams. So I'm going to use my molality formula. It's moles. It's going to be moles of glucose over kilograms of water. Right? So my moles of glucose is going to be 4.35 grams of, I'm just going to say glucose. And what I know is 1 mole of glucose is going to be, let me see, I calculated this earlier, 180.2 grams. This is glucose, and that's going to give me 0.0241 moles of glucose. So that's going to be my numerator up here, 0.0241 moles, and I want to divide that by kilograms of water. So if I have, let me see, 25 milliliters, so 25.0 milliliters, and what I know is the density is 1 gram per 1 milliliter, and let's get this in kilograms. I know that there's 1,000 grams in 1 kilogram. So this is going to be 0.025 kilograms. Okay, and that's going to go here, 0.025 kilograms. And when I divide those out, I'm going to end up with a molarity of 0.965. 4. It looks like I can get 3 sig figs. Molal. Small m, not big M. Big M is for molarity. What it says up here, we're going to calculate molarity using the density of the solution. Okay, so here we have a solution that has a density of 80.876 grams per milliliter, and it has 5 grams of toluene and 225 grams of benzene, and we want to calculate the molarity. So that's big M, and that's moles of solute over liters of solution. Okay, to get the moles of solute, I have 5.0 grams of heptane. And what I know is 1 mole of heptane, I've calculated it already, is 92.0 grams. And this is going to give me 0.054 moles of heptane. I'm just going to call it hep. And I need to figure out the volume. Okay, so I have 5 grams of toluene and 225 grams of benzene. So I have 230 grams total of solution, right? And it gives me the density, so I can use that density to figure out the volume. 0.876 grams is 1 milliliter. And I'm going to go ahead and get this to liters, and 1,000 milliliters is 1 liter. So this is going to give me 0.263 liters. So my molarity is going to be 0.054 moles over 0.263 liters, and that is going to give me a molarity of 0.21 molar. Alright. Alright. So both molarity and molality are similar, but molality is one that is not temperature dependent because it uses kilograms of solvent instead of volume of solvent. So if you know the density of a solution, we can go from molarity to molarity, molality to molarity, and vice versa. So we're going to do one more of these. Okay. So here we have a solution that is 36% HCl by mass, and we want to calculate the fraction of HCl in the solution. And we know it's aqueous, so it means it's got water in it. So let's take a look. So let's assume we want to know the mole fraction. So if it's 36% by mass of HCl, then it's going to be the remaining percentage water. So let's assume we have a 100 gram sample. And if we do, we got 36 grams of HCl, and we're going to have 100 minus 36, or 64 grams of water. So if we have 36 grams of HCl, what I know is 36.46 grams of HCl is 1 mole. So this is going to be 0.99 moles of HCl. And 64 grams of water, 18.015 grams of water is 1 mole. This is going to give me 3.6 moles of water. So my mole fraction of HCl is going to be 0.99 moles of HCl divided by the total number of moles, which is going to be 0.99 plus 3.6 moles, and that's going to be total. And that's going to give me a mole fraction of 0.22. Okay, that's for HCl. Calculate the molality of HCl in the solution. Okay, so if I have 0.99 moles of HCl, so molality is moles over kilograms, right? And what I said here is I'm going to assume I had 100 grams. So the 0.99 moles of HCl assumes a 100 gram sample. So I'm going to assume if I have 100 grams, I have 0.1 kilograms, right? So if I divide that out, no, I just want the solvent, right? So I just want the 64. So I have 64 grams of water, because this is kilograms of solvent. So this is going to be 0.064 kilograms. And if I divide all this out, I'm going to get 0.15 molal HCl solution. Okay. Alright, so we're going to stop there and talk about colligative properties in the next podcast.